Okay, so hi everyone, and welcome to my talk. I'll be presenting what's in the box, which is extending capture checking to handle generic data types properly. And I'm Yichen, and this work is co-authored with Oliver, Nguyen, and my advisor Martin. So generic data types, they are everywhere, of course. They are in real programming, they are everywhere, and they are a fundamental thing. But for capture checking, which is a recently proposed effect and resource tracking system for Scala, it actually remains unclear how it can interact with them. And this work actually fills this gap. And we propose System Capless, which is a new foundation calculus that handles generic data types properly. And it's minimal, it's expressive. And we think it would be a perfect foundation for capture checking and its follow-up extensions. And more importantly, with it, we have a principled understanding of how to track captures over generic data types. And then with the latest Capless-informed capture checking implementation, we successfully capture checked the entire Scala collections library. And we think this is, of course, a key prerequisite for capture checking to be practical. And so maybe first thing first, what is capture checking? And shortly, this is a type system for tracking effects and resources in Scala. And we have quite an ambitious goal. We want to bring effect tracking to all Scala users and not just a research prototype. And this would require, in particular, lightweight notation, minimal disruption to existing code, because Scala is like a highly established ecosystem. And the essence of capture checking is quite simple. So first we have capabilities, and all effects accessed via capabilities. And we represent capabilities as just program variables in our programs. And the second is capturing types. So we argument types to track what capabilities or variables the value will capture. And that's the type we'll talk about the effects of this value. So first, let's talk about capabilities, and it is quite a established idea. For instance, Yichen is famous for using capabilities, and programs will use capabilities to perform effects and access resources. And for instance, here we have a console capability for accessing console I/O and a file capability that provides access to a file in the file system, and a cancel div by zero capability representing the permission to throw a exception, which is a control effect. And these capabilities are represented as the program variables. So for instance, in this program, we assume we have a console capability at hand, and here the caret marks the capability to be tracked by our system, and we can write a greet function that prints a greeting to someone to the console. Okay. Yes. And now we talk about capturing types, and here is the syntax, and there are two parts. So the shape type tells you what the value is. It's an integer or a function, whatever. And the capture sets will tell you what variables or capabilities it might capture and use. And so back to our greeting function, this type will be string to unit capturing console, and the capture set makes the effect explicit that this function may perform some console I/O. And there have been decades of research on the effect system. So why capture checking? Is it like just yet another effect system? So let's recall our ambitious goal that we want to bring capture checking to the mass. And Scala has a quite established ecosystem, a lot of existing code. And this means that we will not be able to start fresh. And we need an effect system that can be retrofitted into established code bases with minimal disruption. And that's what capture checking is for. And to achieve this, there are actually two key ingredients. One is the lightweight capture polymorphism, and the second is boxes. So first, for lightweight capture polymorphism, let's look at the classical map example, list map example in CC. And surprisingly, its signature stays identical to the previous one. And how would that work? Under the hood, so in CC, we have the universal capability cap. And here the T fat RLU is actually an alias for T2U capturing cap. And cap is like the top capability in the system that governs everything in the world. So effectively, every capture set is a subcapture of cap. And here, subcapturing will be like subtyping, but for capture sets and capabilities. So this is analogous how objects work for subtype polymorphism. And here, map is taking a function that could perform any effects. So it's effectively polymorphic over the effects of f. So now let's look at the non-eager version of this mapping operation, the map of iterators. And this capture notation is the only change from the vanilla version. So this signature says that the resulting iterator can perform the effect of the input iterator and also the effect of the function f. So here, the name of f also becomes the effect it will perform. Yeah, so now boxes. So when a capability is put into a box, it will become pure. Like here, when we have a file capability, if we box it, it will become pure. And then to use what is boxed, we must do an unbox. And when we unbox, the box capture set will like be popped out and charged to the environment. Like here, if we write a function that opens the previous box and use the file capability, it will capture f. And this entire process is called capture tunneling. And now we have the key design choice that generic types have always be boxed or pure. And I don't go to the details of this design choice, that they are a key mechanism to ensure the lifetime of capabilities and essential to writing generic operations in a clean and expressive way. So all these ideas have been formalized in CC Sandbox, published in TOPLUS. So far, so good. Then why do we need another new foundation for capture checking? And the problem is when we are actually making everything practical and try to capture checking more and more things, we found that there are more problems. So it's again with generic data types. So CC Sandbox has one restriction that you cannot unbox a cap. And do you see this box impure function? It type says it captures cap, the universal capability. And CC will disallow unboxing this boxed computation. And this rule exists mainly for scope safety, and we don't have time to dive into it too. But the intuition is quite simple, that the cap means everything, and it's just too permissive to allowing unboxing anything. And so to do this restriction, this perfectly reasonable code will not work in the prerequisite system. So here, this make iterator function takes a list of computation, and each is computing an integer. And we want to make this list of computation into an iterator for integer. And I want to know that the parts in gray will not be in the surface language. They are always inferred by the compiler, like all the box types. And we will have the error here that when we try to unbox the computation in the list, its type is actually capturing cap under the box. So effectively, we cannot access what's in the box. So let's have a post-mortem of this failing example. So the intention of this cap in the parameter is actually to convey that this make iterator function should be polymorphic over the effect under the boxes in the list. But because the cap occurs inside the box, this effectively prevents us from accessing anything inside the list elements. So it seems that the CC's lightweight polymorphism is falling short. And in fact, with explicit polymorphism, we can express this function in a natural and a principled way. Like here, we can universally quantify a capture set, and then the resulting iterator will be capturing this universal capture set C, which is precisely what it is. And explicit polymorphism is providing us with a clean solution to this problem, but this is what the previous CC doesn't have, actually. So, and that's why now we have System Capless, and this is a new formalization of the capture checking approach, but it drops the universal capability cap, and instead it's introducing explicit quantification, both universal and existential. And but this is actually going the opposite way of the existing CC system. So recall our ambitious goal that to integrate the effect and resource checking into Scala. So our system must actually be quite non-intrusive and flexible, and that's why CC was advocating for its lightweight polymorphism to avoid the overhead of explicit polymorphism. But now are we going exactly the opposite? But the short answer is not quite. So for the majority of the code, like the list mapping functions we see here, we still want to write it in the implicit style. And we don't want to write code this way, which requires adding effect parameters to every single higher order functions in the library. But on the other hand, when CC's lightweight notations for short, we still want to express these functions, like this make iterator example. So this is essentially a design trade-off. Like on the one hand, we have the lightweight style, which is minimal notation overhead, but the expressive is limited. And we have the implicit style, which has some intrusive notation overhead, but the expressiveness will be optimal. So what shall we do then? So, but why do we have to choose? So we don't have to choose. We can offer both in the system. Then it's up to the user to decide which style to use. So we can use lightweight style when it fits, and when it falls short, we can use the explicit style to regain the full expressiveness. And moreover, now that we have the System Capless, which is like the formalism of these explicit quantification, which have a principled foundation for capture checking, we can also understand all these lightweight notations by a translation to them. And then that's why we also have system rcap, and it formalizes all the lightweight notations we have in capture checking, and they are understood via a type-preserving translation or compilation to Capless. And moreover, we also offer like lightweight notations for capture polymorphism under boxes. So instead of writing the function this way, which is what we've seen, you can equivalently write it this way. And but that doesn't require any explicit capture parameters. And the ops star here is the rich capability of the parameter ops, and intuitively it represents what's in the box of ops. And this new formalism is informing a redesign of the capture checker, and there's no need to read this table. I will explain it to you. So with it, we successfully capture checked the Scala collections library, and the collections library is, of course, really highly generic. But the vast majority of classes do not even need signature changes, like list mapping. We have talked about it. And for the parts that needs signature changes, we need to add more capture notations, but no explicit quantification is needed. The lightweight notation with the rich capabilities we just saw on the last slide is sufficient for capture checking the entire standard library. And the capture check library is already in nightly version of Scala 3, and it will be officially shipped in Scala 3.8. And the credits should go especially to my colleagues Nguyen and Hamza, who did most of the work for this capture checked library to be shipped. And this is a short talk, so we cannot cover everything, but there's some more things. So the metatheory is completely mechanized in Lin4. And furthermore, we have the Capless, which is now a great foundation system for starting various extensions. So there's a lot of extensions that's under development. So for instance, System Capybara, it brings like separation and freshness reasoning to Scala. That's the goal. And I had a talk on Tuesday already. And more things like class capabilities and the interaction between capture checking and the classes, etc. And you can check our paper for more details, and also the website. And thank you for listening.
All right, any questions?
This is on. Thank you for the talk. So I have two questions. I guess the first one is, so I was interested in the fact that, so you added reach capabilities, the explanation for them was great, but I was curious, is there a reason why they needed a separate notation? Is there ever a time when the user writes an annotation, they include a box, and they don't mean the capabilities under the box? Is there a need for the star? For example, if you go back to your example, could you have just written ops? Of course, this means something different, but maybe the user never means I capture the box and not the capabilities inside the box.
Yeah, like the example here.
Yeah.
Sorry, I didn't get the question. Could you?
So the question is, do I ever write an annotation where I capture a box, and I don't mean I also want all the stuff inside the box? Like, do you need a notation that is the star? Because I have just written ops here. Because maybe I just mean I always want the thing inside the box.
So we need a star here because like ops in theory just means like the top level capture set of ops, which
right,
is
but
empty
I mean,
here.
if I'm capturing ops, do I ever just want the top level capture set of ops? If it's a box?
So for instance, consider the operation that concatenates two iterators. So it gives you a new iterator, it does not go inside the box, it doesn't execute the iterator,
Okay.
it just gives you the concatenation.
Okay, yeah.
So that's an example.
Okay, thank you. Okay.
Okay.
With an observation that might actually either convince me I understand this or convince me that I've no absolutely clue. Presumably the unpacking, or what you're allowed to do once you've unpacked, is different. So if you only have a capability for the box, all you can do is get this thing out of the box, and it's not saying you can do anything with, to use the title of the paper, what's in the box. But if you've got the star capability, it's saying not only can I unpack the box, I can do with that's in the box.
Yeah.
Basically, you unpack to do something. So for us, it's the same thing. So basically, you can't unpack the box without representing the capability that's hidden in the box.
So then that goes back to Isaac's question.
Well, a
Okay.
concatenation iterator
Maybe-
can just concatenate the boxes. It doesn't need to go inside the boxes, right? The boxes are the operations that
All right, so let's keep this discussion and thank the speaker again. This is the end of the session.